We move now to a regular register algorithm in the fail-silent model that uses the concept of quorums to achieve regular register consistency. So we call this algorithm the majority voting algorithm. And the main idea is to use the concept of quorums that we described earlier, i.e. a majority of processes has to be contacted. So we always write and read from a majority of processes. And from a majority, we know there is at least one correct process that knows the most recent value. Here's an example where a majority is 5 out of 9, and here is the overlapping process. So again, the quorum principle, we divide the system into quorums. Any two quorums should intersect and overlap, and we try to overlap read quorums with write quorums. And this implies that the number of processes in the read column plus the write column are greater than the number of processes in the system. A majority quorum has both advantages and disadvantages. The advantage is that it tolerates the crashes of a minority of processes, and disadvantage is that a process has to read and write from a majority of processes. So let us now look to the algorithm. Before that, let's introduce the notion of timestamp value pairs, where each process stores the value of all registers. But we will describe this algorithm with respect to a single register. So what is the value of a register R? It is a timestamp value pair, so TSV, and TS is a sequence number initialized to 0 at the writer. A sequence number is just a counter and is incremented at each write. So we use the timestamp to determine which value is more recent. This is important because we need to read the most recent value. Now, at all processes, register R is also a pair, a timestamp value pair, and the timestamp is 0, and the value is some initial value according to the type of that register. Again, each process stores the value of register R with the max timestamp for each register. The max here, the max timestamp that this process has observed so far. The algorithm will be structured into phases. So communication involved in operations are structured into phases. And a phase run by process PI consists of the following. PI, best ever broadcast a request, like here. And PJ, when it receives a request, for example, this process here, it processes the request and then sends a response. So this is the response here. This is the response. PI, then the original process that started the phase, waits for responses from a majority before the phase ends. In this case, if you think about it, P1 will get a response from itself, and it gets a response here from P2. In this case, it has got a response from a majority. Then this is where the phase ends. And responses are done by a reliable channel. So this is an assumption. So we have a best ever broadcast and reliable channel communication. Now, process PI that initiated the phase, after getting a majority of responses, it ends the phase and it ignores all other outstanding responses. So it means here that P1 will ignore this response. So now that we understand what is a phase, so let us look to a write operation in the majority voting algorithm. So a writer will execute this write operation of register R with the value V. So first, it increments its local counter, that is sequence number, that is our timestamp. Then PI, the process that starts the write operation, will form the pair TS and V, where TS is the current sequence number. And then PI will start the update phase by sending update requests for register R with a timestamp value pair TS and V. So here is where process P1 starts the update phase. So any process that gets the request, it will update its register to be the max value between the current value of each register and the TSV value pairs that it got in the message. So this is what happens here, here, and here. And the process PJ responds with an ACK. And then PI, the process that started this phase, the update phase, completes the write when the update phase ends. And again, remember, the update phase will end here when a process, P1, gets a majority of responses. So that's where the update phase ends. And it will, of course, ignore this request. So now let us look to the read operation. So a process PI executing a read operation will start what we call a query phase and send query request with the register identifier. That's what it does here. Each process, for example, P2 here and P3 and also P1, responds to the query with its current timestamp value pair. And when the query phase ends, and it ends at this point, PI picks the max value received. So the max timestamp value pair received. And that will be the result of the read. Again, when read completes, all outstanding responses are ignored, like this one will be ignored. And this could be implemented by tagging the query phase messages with a read identifier. So let us illustrate the majority voting algorithm, and just really to emphasize the point that when a process gets an update, it only stores the update with the maximum timestamp. So let us look to this. So we want to focus in this. When a process updates a register R, it uses the maximum timestamp it has. So here is a scenario on execution with 5 processes. P1 is a designated writer. In this case, P1 does a write and it got a response from itself, from P3 and from P4. And the broadcast request is still in the system to be delivered later to P2 and P5. Now P1 does another write and it gets a response from itself, from P2 and from P3. Now when these requests occur here, this update request will be ignored. It will be ignored because the current value of the register at P2 has higher timestamp than this value. That's why we did this operation, that we take the max. Now, when P2 does a read operation, it reads from itself. It has already the value 5. It reads from P4, which has the value 2 and it reads from P5, which has the value 2, but this value is the one with the highest timestamps, so that is the result of the read. Let us now look to the correctness of the algorithm, and we focus on the validity condition, which says that a reader has to read the last value written or the overlapping write. So we have two cases, and we take the first case where we have no concurrent write with the current read operation. So assume Q invokes a read operation, and this value pair TS and V was the last written value by P, the writer. In this case, the TS, the timestamp, is the highest timestamp value because the writer always increments its timestamp counter. At the time of the read invocation by Q, we have a majority that has this timestamp value pair, TS and V. When Q performs the query phase, it gets at least one response with this last value because of the majority quorum property, and it returns the value V. Now let us consider the second case where the read operation is concurrent with the write, and that write has the timestamp value pair TS and V. The previous write before this write operation will have the timestamp TS minus 1 and the value V prime for arbitrary value V prime. So this is the previous write, and that is prior to TSV value. We know that a majority of processes store the previous write before the concurrent write is invoked. So when we do a read, the query phase of the read will return either the previous write, TS minus 1 V prime, or the current overlapping write, TSV. It will return the previous write, TS minus 1 V prime, if the update phase of the concurrent write is not delivered at any process in the majority consulted in the query phase. Otherwise, there is at least one process with the timestamp value pair TSV, and the query phase will return this pair, and that pair is the one that is going to be adopted. So now let us look to the performance and the resilience of the two algorithms that we just described for regular registers. We had the read one, write all algorithm. The read was local, so the time complexity of the read is just there is no communication, and the time complexity of the write is two communication steps, one for the broadcast and the other for the acknowledgement from each process that is correct. The message complexity is of order n messages, actually it is 2n, and the resilience, which is the number of faulty processes that the algorithm can tolerate, f, is equal to n minus 1. So n minus 1 processes may fail, but the algorithm still satisfies its specification. In the majority voting algorithm, the time complexity for both read and write is 2 communication steps or 1 round trip. The message complexity is of order n, both for read and write. It's actually 2n. Resilience, the algorithm can tolerate faulty processes up to less than the majority of processes in the system. This ends the section on algorithm for regular registers. We have seen that regular registers do not provide a single shared memory view. Still, a process performing a read has to get at least the last value written, which in a sense, a strong requirement in asynchronous systems. We move now to even stronger consistency model, where the distributed memory consistency conditions provide the view of a single physical memory.